Okay, I do apologise for the interruption there. So we were just in the process of defining this random variable big X subscript 1, which is going to map every outcome S onto either 0 or 1. And it's going to map you onto 0 if the first bool up here, so if bool 1, let's say if bool 1 is a white marble, is white, so if it's a number between 1 and W, and it's going to describe it it's going to describe it 1 if the ball is white, and it's going to describe it 0 if the marble is black. Marble is black. I.e., if the marble's number is between W plus 1 and W plus B, then it's going to be a black marble. Right, so you may find this a bit confusing because I thought I was saying order didn't matter. However, you are going to pick the way you're going to write this, you are going to write it with an order. And yes, it's arbitrary how you pick which representative you pick. I could have picked this representative here that I've crossed out. I could have picked that to represent this specific outcome here. That doesn't matter to me. All that matters is that you have picked some outcome, some representative for this particular combination, particular choice of marbles, and that you are sticking by that. So there is a list of these marbles, and you have put one of these marbles first. It does not matter whether you choose to represent it with a different permutation. Obviously the answer to whether x1 is equal to 0 or 1 will depend on which representation you pick. But I'm not interested in these random variables x1. I'm going to basically make a bunch of other random variables to do it all the way through, and I'm going to make x2, x3, x4, x5, which will each describe you 0 or 1 depending on whether your if marble is black or white. And basically I'm just then going to take the sum of them to get x. And basically the sum does not depend on which representative you pick. So do not worry about the fact that, okay, it was kind of arbitrary what order I put them in. That isn't going to matter basically, because although it's going to affect the outcomes of the individual little random variables, these subscripted random variables, we're not interested in the subscripted random variables other than what they can tell us about this big random variable big X. Okay, so don't worry about the fact that, okay, yes, the order in which I put these was kind of arbitrary. Okay, so x1 is going to describe your 1 if you've got a white marble in your first position, and it's going to describe your 0 if you've got a black marble in your first position. So in this case, we've got a white marble in our first position, and we'd be ascribed a 1, basically, by this random variable. So this outcome would be ascribed a 1. However, you might say, the thing I was getting at just before is, isn't this equivalent to having W plus 1, 1, 2, W, and then W plus B, which is helpfully, there's a W there. Yes, I would say yes, it is equivalent, and yes, I only wanted one of these in this whole sample space, so I didn't want degeneracies. And yes, this will ascribe you a 0, but it won't matter. It won't matter for our purposes, because what we're going to do is define more random variables, and we're not interested in these individual ones. What we're interested in is the sum, and the sum isn't going to be affected. So let me do that and show you what I mean. So now let's create the random variable x2, which is going to ascribe you a 0 or 1. And x2 is going to ascribe every outcome s. It's going to ascribe it 0 if the second marble is black. Second marble black. Okay, so let me pull this out. And it's going to ascribe it 1 if the second marble is white. So if I'll just put if white. Okay. So in this case here, if we're using this representative to represent this specific choice of marbles, you would ascribe a 1 again to x2 would describe this outcome a 1 because the second marble was a 1. Okay, and then you go on and on and on. You make x3, x4, x5, and you go all the way down to x to the x little n, which is again going to ascribe you a 0 or a 1. And basically, it's going to ascribe you, again, it's going to ascribe you 0, so it's going to ascribe an outcome 0 if the nth marble is black, so nth black, and it's going to ascribe you a 1 if the nth is white, a white marble, basically. Okay, and basically, this random variable x, this random variable which ascribes to every outcome the total number of white marbles, can be viewed as just being the sum of all of these little random variables, x1, x2, plus all the way up to xn, so all of these subscripted random variables, because each one of these is going to ascribe a 1 if there's a white marble in the ith position, basically. So if you sum all of those up, you're going to get the number of 1s you get is going to be the number of white marbles you overall have, and the number of 0s you get is going to be the number of black marbles you have. So that's going to tell you, when you sum it all up, how many white marbles you overall have. And that's why I do not care about the fact that you could have, the choice of representative for this outcome is arbitrary. You could have put them in any order, because yes, okay, the individual random variables will change, but this sum will not change. So yes, okay, this will ascribe x1 would be for this representative here will ascribe this representative a 0, and it will ascribe this representative a 1, and that seems sort of like, okay, we haven't defined it very well because we've got the same thing being ascribed different numbers, but basically this sum overall will ascribe you the same value, and in this case it will ascribe 3 to this one and it will ascribe 3 to this one because it's going to equal the number of white marbles, which doesn't depend on how you permute the numbers you've picked. Okay, so now that we've discussed that, what we can do is we can say that the variance of this random variable big X is equal to the variance of this sum, basically. So I can put in x1 plus x2 plus all the way through to xn. So that's kind of hopeful, because we can now use the fact that the variance is equal to the covariance of a random variable with itself. So the variance of any random variable, so let me just remind you of this, the variance of a random variable A is equal to the covariance of that random variable with itself. So now I just stick in this sum as our random variable A, and I get that this is the covariance of x1 plus x2 plus all the way through to xn with itself, x1 plus x2 plus all the way through to xn. And now what we do is we apply the distributive property of the covariance and say that this can be expanded out as well, we could originally expand it out as the sum I is equal to 1 to n, the sum I is equal to, I'll say j is equal to 1 to n of the covariance of xi, xj. And basically what that's saying is go through and do the covariance of x. So for each, if we make a table here, what this is saying is let I equal 1. So the vertical line is going to represent the possible values of I, and then the horizontal line is going to represent the possible values of j. So we've let I equal 1, so we get the covariance of x1, and then we let j vary over every single value from 1 to n. So we do covariance of x1 with x1. So that's 1. Then we do the covariance of x1, we fix x1, and then we let the j vary, so we go up from j is equal to 1 to j is equal to 2, so that's 2, 3. We then have the covariance of x1 with x3, etc. And we go on all the way down to n, which would be the covariance of x1 with xn. So we get there, and then we'd say, okay, now we'll change I to 2, and we'll do the covariance of x2 with x1, and we'll add it on. Basically what we're going to do is sum up all of these terms. So we're going to add all of these terms together, and then we'll get the covariance of x2 with x2, and then we'll go on the covariance of x2 with x3, etc. And we'll go all the way down to the covariance of x2 with xn. Okay, so basically what we can do is we can simplify this sum, though, because these diagonal terms here, let's look at these diagonal terms firstly, these covariance of x1 with x1, the covariance of x2 with x2, and then of course you'd have more, so you'd have the covariance of x3 with x3, the covariance of x4 with x4, all the way down to the covariance of xn with xn. Okay, but by this thing up here, those are all equal to just the variance of the individual. So we'll say this is equal to the variance of x1, this is equal to the variance of x2. So we could write this sum, we could take these diagonal terms out and write it that it's equal to the sum I is equal to 1 to n of the variance of xi, and that's just basically taking account of the diagonal terms. But then we need to add on all of these off diagonal terms here. However, notice another thing, another interesting thing, that this off diagonal term here covariance of x1 with x2 is equal to this diagonal term off here, which is the covariance of x2 with x1. And similarly, if we put another term here, so for 3, we get the covariance of x3 with x1, that is going to be the same as this off-diagonal term up here, covariance of x1 with x3. So basically, all of these off-diagonal terms above, let's say to the right of the diagonal, have a corresponding off-diagonal term to the left of the diagonal. So we could just say that this is plus 2 times the sum of all of these terms are up here, basically. So we can say, let's get rid of all these terms down here and just multiply all of the, let's sum up all of these terms up here and then just multiply it by 2 and we'll get the off-diagonal terms down here, basically. So, if we want to sum over all of these terms up here, the way we do it is we note that the horizontal component, this j component here, the second component here is always greater than the vertical component, i.e. that this number here, the x2, this 2 is always greater than the 1. If we look here, we've got 3, which is greater than 1. So the component in this second position is always greater than the component in our first position. So basically, this is going to be the sum, I is less than j, of the covariance of xi with xj, where you try and vary I between 0 and, between 1 and n, and you try and vary j between 1 and n. And I'll show you exactly why that sum is equal to the sum of all the all of these off-diagonal terms above the diagonal. So if you start, the way you'd start is you'd say, okay, start with I is equal to 1. So we'll let I be equal to 1. So that's going to give us this row here. Okay, and now I let j take on all values between 1 and n such that this condition is also satisfied. So if I ask, can I do j is equal to 1? No, I can't, because 1 is not less than 1. So you do not allow j is equal to 1. So you do not sum over covariance of x1, x1. So you do not get that term. Then you say, okay, try j is equal to 2. And that, bingo, that does work, because 1 is strictly less than 2. So we get the covariance of x1 and x2 is an allowed term. So we get this term here. And then we go on. And all the numbers after that, 3, 4, 5, they do satisfy this property because they are all greater than 1. So we'll sum up all of these terms along here. Okay, and you go all the way up to n, which, so you'll go all the way down to there. So you'll get this entire row from this diagonal term here onwards. Okay, then you'll say, okay, let I now equal 2. So we go on to the second row. Now, j could equal anything from 1 to n, but it has to satisfy this condition. So if we try j is equal to 1, well, that's certainly not true. 2 is certainly not less than 1. So 1 goes out, so we don't add on that term. Then we ask, what about j is equal to 2? Again, that term goes because 2 is not strictly less than 2, so you don't get this term. But then when you get to j is equal to 3, you do, this condition is satisfied, 3 is strictly greater than 2, so we do sum up this term here, and we go on, because all the terms after that, 4, 5, all the way up to n, do satisfy that. So I hope you get the pattern now, that basically what this is going to do is it's just saying, sum up all of these terms that are to the right of the diagonal term, like that, basically. Okay, so if we want to work out the variance of our big random variable x, which is hypergeometrically distributed, all we need to do is work out the variance of these individual these little random variables, these subscript random variables, and basically we need to add that to 2 times the sum of all of these covariances of these random variables xi and xj, so these subscriptive random variables. Okay, and we'll continue this discussion in the next video.